Motion in space.
Yes, motion.
So it's like this. You gotta have this music when you go through space. You know what I'm talking about?
You have a whole bunch of.
We do not have a hole punch in this room, but I think there's one in the math tank, and I know there's one in Nina's office. For my class?
Whenever you're doing something in
Nice.
space.
Because I ran out of paper.
You doing the Star Wars music?
It's a new meme.
So on Tuesday,
Wait.
I don't consider that space music.
You haven't heard this?
I've seen that video.
It's like when somebody falls or like they jump in the air.
They jump
They
off.
just take they freeze it when they're jumping. And you play that music, and it's just got them going through different places, like through space.
No.
And then, like,
Is this like the new planking?
no, it's just like a new meme. It's the new meme.
Okay.
Meme of the month. Meme of the month. MOM. Did you see the one where they get hit by a tire? Like the tire just comes out of nowhere and smacks him into the ground, and it's just kind of going like this.
Well, let's not forget the one where the guy jumps a Toyota.
All right. On Tuesday, we covered 11.6. We did not have a video, though, because we did not have a lecture on 11.6. 11.6 was calculus of vector valued functions, and I just had you guys do a worksheet. Because calculus of vector valued functions is pretty much just calculus 1 on the individual components. So if you remember how to do basic derivatives and basic integrals, then all you have to do is apply that to the individual components of the vector. Right?
Calculus times 3.
Yes.
That's what's called calculus 3, right?
Yes. So, Tyler, I will get you a copy of the worksheet. And that's really all that was in 11.6. So in 11.7, we're going to talk about motion in space. Those last couple of problems on the worksheet didn't just say find derivative, find second derivative, do antiderivative. They actually said find velocity, find acceleration, because those are the applications for first derivative and second derivative. So in 11.7, it's going to go more in depth into velocity, acceleration, speed, things like that. Okay? And we're actually going to look at projectile motion. So for those of you who have taken physics and done the projectile motion stuff in physics, we actually do it completely different in here, unfortunately. From my experience in the past, from what people have told me, because they ask me, can I just do it the physics way? They usually end up getting it wrong when they try to do it the physics way. And they would have if they just do it the way that I showed them to, they'll get it right. And then they like say, can I just do it the physics way? And then they end up getting it wrong.
All right, I'll try the physics.
So you're more than welcome to do it the physics way if you already know a way to do it. But just you have to make sure you get it right if you do it that way. Make sure you really know that way. If you still are fuzzy on that way, then maybe learn my way. Maybe my way will make more sense. Maybe I'll explain it more. I don't know. We'll see. Okay. So some of this is really just hopefully familiar, just the basic relationships between position and velocity and acceleration that you already know. So if r of t is a position vector, r prime of t is velocity. And we'll sometimes give it its own name. We'll call it v of t. And then our double prime of t is going to be acceleration. And again, we might actually give it its own name. So our double prime of t is v prime of t. We might call it a of t. So most of us know this already. Yep. One more.
Have you ever used that in calculus? Jerk.
No. And we're not going to write it up, but there is an application for third derivative, and it's jerk.
Do we do that in physics at all? Or would we do it?
Just in that section.
No.
The magnitude for r prime of t, all of these are vectors. As when we saw on Tuesday, taking the derivative doesn't change it to a scalar. You're just taking the derivative of each of an individual component, but you're still writing your answer as a vector. So r prime is still a vector. R double prime is still a vector. So velocity is a vector. Acceleration is a vector. If we do the magnitude of r prime, which is the magnitude for your v, just the magnitude portion of your velocity is what? Speed. Because velocity has two components. It has speed and it has direction. Yep, so just the magnitude of your velocity is speed. So in real life applications, usually what we know is acceleration, because most of the time acceleration is due to gravity, and then we'll know some initial conditions. We'll know an initial velocity that we apply on an object, and we'll know an initial position that we apply on an object. So for most practical applications, what we're going to be doing is working backwards. We'll know acceleration, and we might want to use the acceleration and use those initial conditions to work backwards to a position function. We won't necessarily know just some random position function for something, just out of thin air. So if we know acceleration and we want to work backwards to position, so knowing the relationship between these three functions, what calculus operation would we use to go from acceleration back to position? Antiderivatives. And we'd have to do them twice. And remember, with antiderivatives, if you're not evaluating over an interval, it's considered an indefinite integral. And we would have to use our initial conditions to solve for that arbitrary constant. The problems we did on Tuesday, we always evaluated, so we didn't deal with any arbitrary constants. It might be beneficial for us to look at a couple that have arbitrary constants so you can see what to do if arbitrary constants come up. And then we'll look at a couple of examples of how to work these backwards so that we can go from an acceleration to a position function and use those initial conditions to solve for the arbitrary constants. So we can use acceleration and initial conditions to find velocity and position functions. So before we do that, one quick example of an integration problem where we don't have bounds to plug in, and we're going to end up with arbitrary constants. If we were asked to integrate ti plus 2t minus 5j plus e to the 2tk dt. Remember, we're going to treat this really as 3 different integration problems, which means we're going to have 3 different arbitrary constants. The I component is going to have an arbitrary constant, the J component is going to have an arbitrary constant, and the K component is going to have an arbitrary constant. And there's 2 ways to write that. We're going to do integration rules just like normal, just like we would have done in Calculus 1. But we're writing the answer still as a vector. So we need to integrate t. What's the antiderivative for t? 1/2 t squared plus an arbitrary constant. But I'm going to have 3 of them, and they could all potentially be different. You could do A, B, C. What I'm going to do, and what you're probably going to see most often, is C sub 1, C sub 2, C sub 3. But that's perfectly fine. A, B, C is perfectly fine. Okay, as long as there's a way for us to show that they are arbitrary constants and that they are potentially different numbers. We don't want to say plus C plus C plus C, because that means they're all the same C. But what you're probably going to see most often is C sub 1, C sub 2, C sub 3. So this is our I component, 1/2 t squared plus C sub 1I. We didn't do this on Tuesday because we had values to plug in. So we don't do arbitrary constants when we have values to plug in. And then we'll integrate our J. We want to integrate 2t minus 5. T squared minus 5t. And then it also needs its own arbitrary constant because it's a second separate integration problem. Bless you. So we're going to say plus C sub 2. That's a parenthesis. Doesn't look like one. That one's not much better. There. And then we're going to integrate for our K component, antiderivative for e to the 2t. Nope. It's going to have an e to the 2t in it.
Is it Ln?
Nope.
It's the same thing.
The derivative and antiderivative for e always contain itself. For derivatives, you have to do the chain rule, which means multiply by the derivative of the exponent. So that's what Eason did. He multiplied by the derivative of the exponent. Antiderivatives are the opposite operation. So if in derivatives you multiply by the derivative of the exponent, what do you think you're going to do in antiderivatives? Divide. It's a half of e to the 2t. Plus c sub 3. Okay. So you're very close, Eason. So since we treat this as 3 separate integration problems, there are 3 separate arbitrary constants. And sometimes you see them incorporated right there into the original vector. Sometimes you see them separated out as a separate constant vector. So another way you might see this is 1/2 t squared I plus t squared minus 5t j plus 1/2 e to the 2tk. So those are just our straightforward antiderivatives. And then you might see then a constant vector, c1i plus c2j plus c3k. I don't like that, because if we need to now solve for c1, c2, c3, we really need it incorporated into these other pieces, because to solve for c1, c2, c3, we've got to plug something in for t and then see what's left over. And having i's in two different spots and j's in two different spots, we're going to end up combining them back together eventually anyway. So me personally, I like this way, but you might see it either way. And when I post the homework, you're in the homework, in the integration problems, they're just going to ask you to do this piece, and they're going to have this piece already done for you. It's going to say, there's going to be a blank box, and they're already going to say plus C1I plus C2J plus C3K. They're already going to do that part. So you're not going to have to do arbitrary constants. MyLabs Plus is already going to fill that spot in. But if we have to use this to go any further, to do anything else, this is really I think, the better option. It's more usable. So Tyler, this is like what we did on Tuesday, just applied basic calculus 1 rules on individual components. So if we had an acceleration function and we wanted to go backwards to eventually get a position function, we would have to integrate and then use some initial conditions to solve for those arbitrary constants. I'm sorry. You just randomly started brushing his hair.
You talking me? You were laughing at me? I found a brush.
I found a brush.
I'm trying to brush his whole bag. I was like, you know what? My hair might be messed up. Let me brush it. I want to look good for Kirby.
Okay. All right.
Freak.
I started my prednisone. It's been good so far. I'm full of energy. I did not have to take a nap yesterday. Usually I go home and take a nap.
You're not taking my amphetamines?
No, I'm not taking amphetamines.
Just like pots. You feel like you had a lot of energy.
I'm still making pots.
It's always good. All pots.
Surprised you didn't give us a font t-shirt.
I don't think you guys would appreciate my pots.
I didn't appreciate unless I can. Unless there's a practical use for that pot, you know what I'm saying?
You have like range pots and then like loud pots. It's really loud for a pot.
You think you could make like a pot? It's got like a little globe on the end, and it's got a long stem. You can make that like a vase. Like a what?
Bomb.
No. It's like a vase.
Recording.
Oh.
Poor Hannah's just gonna be like, what the hell?
Put this one on YouTube.
All right, A of t is negative 32. This is just going to be in 2 dimensions right now. It's negative 32j.
She can't hear herself. Can she?
Has anybody listened to these videos?
No.
You really
Post
can't
them?
hear you guys at all.
Post them?
Yeah, they're all on our Moodle page.
I can only use when I listen to them once I kind of hear like slight mumbles in the background.
Mhm.
Like no static.
Yeah, can't really hear you guys at all.
Until she said something about a conversation.
A of t is negative 32j. V of 0 equals, let's say, 40i plus 40j. And S of 0 No, r of 0, sorry. Ten J. What? I'm going to show you a picture of what exactly this means. We have acceleration acting downwards on an object. Negative 32J. It's acting downwards on an object. Initial velocity is pointing in a direction of 40I plus 40J. So that's exactly halfway through the first quadrant. And initial position is 10J. That's 10 units up the y-axis. So if I say this is 10, I've got some object sitting right here. If it's a projectile, when I shoot it, I give it an initial velocity of 40I plus 40J. So it's at what angle is that? If those two components match, it's 45 degrees. If those two components match, it's 45 degrees. I'm shooting it at an angle of 45 degrees, and I can find the magnitude to see angle of 45 degrees at a specific magnitude. And there is an acceleration constantly, the whole time it's in flight, forcing it down at negative 32. So what we're trying to do is derive the formula for the position of the object at any time. Okay, I only know the position that it starts from. That's the only thing I have control over. So that's the only thing I truly know, is where I'm starting it at. And I also know what initial velocity and angle I'm starting it at. What happens after it leaves my hands, I have no clue. But I do know the only thing acting on this is acceleration. So we're going to work backwards from acceleration to figure out what that position path is. Right? And it's just antiderivatives, because the relationship between acceleration, velocity, position is just all derivatives and antiderivatives. What do you know about projectile motion? Not a whole lot?
Not a lot. I learned a lot.
What shape is it usually in? It's a parabola. If we can just ignore all other outside factors, it's going to be in the shape of a parabola. So if we can get that path of motion, we can answer a whole lot of questions about this projectile. The bottom, the horizontal axis is time, and the vertical axis is going to be height or position. Actually, well, we can figure out its maximum height. We can figure out when it hits the ground. We can figure out how far it's traveled when it hits the ground. There's a whole lot of stuff we can figure out just by knowing that acceleration is acting on it. It started 10 units high, and we shot it off at a 45-degree angle with so much magnitude. So we can figure all that out. So all we're going to do is going to go backwards with negative 32J. We ready? Just integration. Not ready? I think you are. You don't need a break yet. It's only 1:50. So be really careful because there's a missing term here, and we are integrating with respect to t. There's no force acting on this projectile horizontally, but we still need to integrate the I term. What is the I term right now in the acceleration function? No, not 1. It's 0. It's the antiderivative of 0. What has a derivative of 0? Any constant. So we're going to have C1I plus, what's the antiderivative of negative 32? Negative 32t plus C2j. This is the starting point for which function? We go back one antiderivative from our acceleration, what does it take us to? Velocity. This is the starting point for our velocity function, but right now it's still got arbitrary constants in it. So now we can use those initial conditions to solve for those arbitrary constants, because we were told that v sub 0 should equal 40i plus 40j. So if we plug 0 into ours, we're going to plug in 0 and compare it to the initial condition we were given. Plug 0 into the one that we got. We're plugging 0 in for t. We get C1I plus C2j. And we were told this should be 40i plus 40j. So C1 equals 40, C2 equals 40. So now we know what the real v of t is. V of t is 40i plus negative 32t plus 40j. All I did is I went back up here and replaced my C1 and C2 since we just figured out what they were. And we're going to do the whole thing over again because we're trying to get to position. And position is another antiderivative back. And we have another initial condition to help us solve for another round of arbitrary constants. So that whole process we just did, we just do the whole thing again. But this time our starting point is v of t. So the antiderivative for 40, no, that's derivative, is going to be 40t plus C sub 1. And then antiderivative for negative 32t plus 40. Plus 40t plus c sub 2j. This is the starting point for our r of t. But there's still arbitrary constants in there. So we're going to go back to the initial condition. They told us r of 0 is what?
10J.
R of 0 is 10j. So we're going to plug 0 into ours and compare it to 10j and use that to help us solve for C1 and C2. So if we plug 0 into ours, we just have C1i plus C2j, because it's a polynomial. 40t is going to be 0, negative 16t squared is going to be 0, 40t is going to be 0. And according to the initial condition, this is supposed to equal 10j. So what does that say about this new round of arbitrary constants? C1 is 0. C2 is 10. And if we rewrite our r of t with those values plugged in, we'll have our position function. So r of t equals 40t. Since C1 is 0, you don't need to say plus 0. R of t is 40ti plus negative 16t squared plus 40t plus 10j. When I was labeling this graph, I started to hesitate, and there's a reason why, because I knew I was doing it wrong. This is not t, and this is not r of t. Huh? I'm sorry. I started to stop myself, and then I was like, let me just wait a second and finish out this problem first. This is still x and y. And the reason is this vector valued function, remember, we can separate it into parametric equations. This vector valued function tells us two different things. It tells us what's going on in the x direction over time, and it tells us what's going on in the y direction over time. So if we just look at the I component, we can see what's going on in the x direction over time. If we just look at the j component, we can see what's going on in the y direction over time. So it's still an xy plane. But now we've incorporated t into the problem. So back in algebra class, we did some fairly simple projectile motion problems where usually t is not used in the problem. Or if it is t, it's just t in height, and horizontal motion's not included. But now this is what's happening horizontally. and this is what's happening vertically. And T is linking them together, so we can answer questions that have to do with both of them, like the range of the projectile. That's one question that has to do with both of them. So let's talk about range for a minute. If I asked you what the range of an object was, how would you interpret that?
The highest one.
It's not the highest Y value, that's the max. That's maximum height.
0.
Minimum to max, that's like a statistical range. That's like a statistical range. This is more of like an application, like the range of a baseball. Like if you hit a baseball, or if you throw a frisbee. No. Has anybody ever gone to the range
How
before?
far you can hit it? Just
Yes. Range is maximum horizontal distance. It's how far it goes before it hits the ground. Okay? It's how far it goes before it hits the ground. It's the horizontal distance traveled when it hits the ground. What?
Bigger rat and how carrying the range is unlimited.
Oh, I thought we were talking about baseball. So what are you talking about?
Oops, I don't know about you.
So the reason that this links both of those equations together is because we're talking about hitting the ground. What's the height when you hit the ground? 0. So hitting the ground means y equals 0. We're interested in knowing what's going on when y equals 0. But the answer to this question is the x value when y equals 0. So first you have to figure out when y is going to equal 0. And then once you know when y is going to equal 0, you take that time and you plug it into the x to see how far x has gotten in that amount of time. So this is one of the questions that links those two equations together, those two components together. So other questions they ask us about projectile motion have to do with maximum height. That one only deals with the vertical equation. When it will reach its maximum height is just, and what is the maximum height, those are just vertical equations. And then they can ask us when it reaches a specific height. That's just vertical equation. But I wanted to address range specifically because in the past it's one that I know people have had the most trouble with. So I knew that there was going to be trouble with it. That's why I wanted to talk about it. So we're going to calculate the range for this projectile that we just got the position function for. And then we're going to have a break. Okay? We want to know the range. So first we need to know when it's going to hit the ground. Because the range is the horizontal distance that it's traveled once it hits the ground. How far has it gone? So if you look up here at our graph, once it hits the ground, we want to know how far has it traveled. So step number 1 is figuring out when it hit the ground. Step number 2 is take that time and plug it into the x equation to see how far it traveled. So we're going to take the y equation and set it equal to 0. That'll tell us when height is equal to 0. So negative 16t squared plus 40t plus 10 equals 0. Now I'm nearly certain that thing does not factor. If you want to work it out by hand, you can do the quadratic formula. Or you can plug it into y equals and look on the graph and see when it has its zeros. I'm sure it's going to come out to be some strange decimal. One of the answers is going to be negative. And we're just going to throw that one away because we're just moving forward in time with these application problems. If you want to work this out by hand and do quadratic formula, t is negative b plus or minus the square root of b squared minus 4ac all over 2a.
I got negative. So, 0.2.
That one we can throw away.
And then 2.73.
2.73. So there are two answers, but one of them's a negative number. We can throw that away since we're dealing with time moving forward from 0. This projectile is going to hit the ground after about 2.73 seconds. We want to know the horizontal distance that it has traveled in that time. That is the range of the projectile. So once we know how long it takes to hit the ground, we'll then take that number and plug it into the x portion of our vector. So the x portion of our vector was just 40t, right? Yeah, it's just 40t. All we have to do is multiply that number by 40. Yeah, it's usually the y piece that's so complicated, and that's because our acceleration it starts off with the y component. So it's the acceleration piece that usually gets up to be a quadratic. Uh-oh.
109.2.
So this particular projectile is going to travel about 109, and we didn't put units on this, but maybe 109 feet, 109 meters, 109 kilometers, whatever.
Hope it ain't flying 109 kilometers.
Could,
It's like a freaking giant artillery gun.
maybe. Centimeters.
Usually meters.
Nanometers.
All we knew is that gravity was acting on it. We started it 10 units high. We angled it at 45 degrees, and we gave it a certain amount of initial velocity. That's all we knew. And we're able to figure all this stuff out. Now, of course, in real life, there's other things acting on it besides gravity. There's going to be other air resistance and drag and wind shear and all sorts of other stuff. Yeah. We just completely disregard those in Calculus 3. You might consider those when you get into upper level physics classes.